Okay, so now that we talk about the Rayleigh dissipation function, I think we're ready to analyze a more realistic physical system. So here we have a simple pendulum. It has length L. The rod is negligible with respect to the mass here. But in this case, what is different is that we have air resistance. So air resistance is actually damping the energy that is present at any point with respect to this pendulum. So you can imagine that the oscillations are actually going to decay with time until it comes to a complete rest. Now, if we draw the Newtonian picture, what we do is we have the free body diagram, and these are all the forces acting on the system. So what we can do is we can take the sum of the torques about the point of rotation O, and then basically we know, well, if we assume this is the positive orientation, then our acceleration is going to be in terms of the tangential acceleration here. And then for this case here, we're going to have the following two forces. We're going to have, well, this is going to be a torque. We have this force times the distance. And then we have the air resistance, which is going to oppose the motion of this. So it's always going to point in the opposite direction to this, times L. And now what we do is, because we know this is rotating about a fixed point, and the radius is remaining constant, we can use the following two equations here. So we can have the acceleration, the angular acceleration in terms of the tangential acceleration over the radius, and then tangential velocity becomes radius times angular velocity. So put those back into the equation and you get to this point here. So that's going to be the equation of motion for this system. And notice that this constant C here is the damping constant, and it is related to the air resistance or air drag. In general, there are different functions that you will find for different types of air drag and all that. If you do fluid mechanics, you will get more into that. But this is a very general way in which we can represent a damping force. So air is just a fluid, and the fluid is absorbing energy as this rocks back and forth. So essentially, we can model it using a damping force like this one. Now for the Lagrangian, what we want to do is we want to use the following equation. So we have Lagrangian here, some generalized coordinate, plus the Rayleigh dissipation energy. We're going to differentiate that, and then this should all be equal to this. Okay, so this is the equation that we want to use to derive our equation of motion. So first things first, we need to define this system in terms of a set of axes. So basically, if we look at it here, what we can do is we can change this to polar coordinates. So x is equals to L times sine of theta. So the reason for that is that if we look at the way that the angle is defined here, we know that the horizontal component is going to be related to the sine of the angle. And then for y, we're going to get the following. If y is being essentially taken from the bottom here, where the total maximum distance is just the length, then the total displacement here is just going to be L minus the horizontal component of this displacement. So this is going to be L minus L cosine of theta. And now in order to obtain the dissipation energy, what we need to do, and also the kinetic energy, we need to obtain the following quantity. So we need the velocity square, which is essentially this term here. So first things first, let's find the time derivatives of these two functions. So we have L sine, so this is going to become cosine of theta, and we're going to take out the theta, so this is cosine theta here. And now for y, we're going to have the following, so this becomes 0, and now we have minus times minus, so it becomes L this sine theta by using the chain rule of differentiation. Now we square those two terms, so the velocity squared becomes L squared angular velocity squared, and I believe, no, that's it. And then we're going to have cosine squared. So we're going to factor out those two terms plus sine squared theta, which we know reduces to 1. So this becomes L squared theta dot squared. So that's the term for the velocity. And now what we're going to have is, well, we're going to have the following. The kinetic energy of the system is going to be equal to half of m times velocity squared. So this is going to be half of m L squared theta dot squared. So this is basically what we have here. Now the next thing that we need to do is we're going to define the potential. So this is just going to be mg y, which is going to be mg L times 1 minus cosine theta. And finally we define our dissipation energy, which is going to be half of c times the velocity squared, which is once again just going to be the following. We have half of that c constant, and now we have this term here, so L squared theta squared. So now what we can do is we can put all of this back into this equation. So let's start differentiating our terms. We're going to have the following. So if we start with this term, we're going to have, oh, first of all, let's write the Lagrangian. So Lagrangian equals t minus v. So let me just do that here at the bottom. Very important step, never skip actually defining your Lagrangian. So Lagrangian in this case is going to be a function of 3 variables, t, and it's going to be equal to t minus v, which is in this case half of ml squared theta dot squared minus mgl 1 minus cosine of theta. Okay, and now this is what we're going to differentiate. So we start off by partial of L with respect to theta. So we're going to have the following. This becomes 0. This term here, well, this times that becomes a plus. But then we differentiate this with respect to theta, becomes minus again. So this becomes minus mg L sine theta. Okay, so now the next thing we're going to do is we're going to find out what this is. So differentiate with respect to the velocity. And in fact, I'm just going to do it straight away. We're going to have the time derivative of this, which is going to be the time derivative of whatever quantity we get in here. So we're going to have the derivative of the Lagrangian with respect to velocity. That's just going to be ml squared theta dot, and then this is just going to be ml squared theta double dot. And then finally, for our dissipation energy, we're going to have the following term. We're going to differentiate with respect to the angular velocity again. So this is what we had. So if we differentiate with respect to the velocity, we get cl squared theta dot. So now if we go back to the original Euler-Lagrange equation, we're going to obtain the following equation of motion. So we're going to have ml squared theta double dot. So this is going to be for that particular case. Now for this here, well, to that we're going to add the dissipation energy term, which is going to be this one here, plus cl squared theta dot equals to minus mg L sine theta. Now we rearrange this, so let's divide both sides by ml. So we're going to have theta double dot equals to minus g sine theta. This is going to be g over L because we have L squared here. And then we're going to have minus c times theta dot. And this is going to be over m, of course, because we divided by ml squared. So this is going to be the equation of motion. So now I believe we made a mistake in the Newtonian one, because I think this should have been ml squared, and then this L should not be here. So once again, I made the silly mistake. Let me just show you where the mistake is. And then this should be g over L here. So it's good that we tried both methods, because I was actually able to point out where the mistake was. So when I substituted back in here, I substituted in terms of this. So for some reason I forgot to take into account the fact that we had L, but remember this is tangential velocity, so we need to rearrange this in terms of tangential acceleration. And then multiply this by L. So when we put that in here, this becomes L squared times theta double dot. And then obviously when we divide both sides by this equation here, then we get this. And this is the equation of motion of the system. And if we compare it back with the Lagrangian formulation, we notice that we get exactly the same equation. So if your system is simple enough, I think I always recommend doing both the Newtonian and the Lagrangian approach, of course assuming that it is possible to do both, because that way you can actually compare whether your equations of motion are correct. Otherwise you wouldn't be able to tell, especially if you make silly mistakes like me. I mean, you wouldn't be able to tell right away until you actually try to model this on, say, a computer simulation or something, and it didn't really give you accurate results. So it's very important to know how to do both methods to check your answers against one another. But this is the gist of how you use Lagrangian mechanics with dissipation energy involved. So basically dissipation energy can be given by anything from friction to air resistance or air drag, and everything can be modeled in terms of a damping constant times the velocity of the object. And we're going to continue with more examples in the next video.